Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. This is the question show, your chance to ask me any questions about space and astronomy. So wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, we've started a new community event on our Discord server. Once a week, we will be doing a live conversation about topics in space and astronomy, space tourism, the future of the International Space Station, planetary protection, things in astronomy. And it's a chance not just for me to talk to you, but also for us to talk together. So there'll be a link to our Discord server if you want to check that out in the chat. And you should come and join us. We're going to be doing this every Wednesday, as well as any special live events. All right. Let's get into the questions. Murdoch rules. Hey Fraser, when you're talking about Venus, it got me thinking, is there a geostationary orbit that you could put a satellite in around Venus? Given its day is so long, would the satellite need to orbit at some extreme distance if it is even possible? That's a great question, and I had never thought about that before, but absolutely. There is a point where a satellite could hover directly over top of some spot on Venus. And we have these here on Earth, the geostationary satellites, but they're in the 40,000 kilometer range, and once a day they orbit around the Earth and return back to their original point at the exact same rate that the Earth is turning. And so you get it as if from our position here on the surface of the Earth, it looks like the satellite is just hovering motionless in the sky. But Venus takes 243 days to turn once on its axis, and it does it backwards. Not that that really matters, I guess. So you definitely need to be a lot farther because it's going to take a lot longer. And I did a calculation. Your satellite is stationed out at 1.5 million kilometers away from Venus and slowly rotates at about half a kilometer per second. It will remain and hover directly over that. And really, any planet that rotates, it's going to have one of these orbits, these geostationary orbits. You can imagine exoplanets are all going to have them. So 1.5 million kilometers, so just to give you a sense, right, like the moon is about 400,000 kilometers. So that's like almost 4 times the distance from the Earth to the moon. But still, it's possible. Bravo01. My question is whether Israel violated the Outerspace Treaty by sending tardigrades to the moon on board the Beresheet spacecraft. And if so, why did SpaceX allow them to launch using the rocket? Should there be consequences, considering how NASA tries to sterilize all of its missions before going to Mars and so on to avoid contaminating the planets with Earth's bacteria? Right. So Israel sent its mission to the moon, and they were going to be landing on the surface of the moon with the Beresheet lander. And we all watched this in real time as the lander attempted to make the landing, and it failed and it crashed. And we learned later that there was a experiment on board that was containing a bunch of tardigrades. And according to some scientists, the tardigrades probably survived the impact onto the surface of the moon. And tardigrades are nigh unkillable, capable of hibernating when they are in extreme situation like lack of oxygen, radiation, no water, etc. And so theoretically, the tardigrades are just hibernating up there on the moon, waiting for some fool to give them a nice warm environment where they will return and, I don't know, water bear cute them to death. So is it a violation of the Outerspace Treaty? No. The Outerspace Treaty really was developed to stop nations from hovering nuclear weapons over top of each other. That's like most of the Outerspace Treaty is, let's make sure that nobody puts nuclear weapons into space and orbits them over planet Earth. Because you can imagine, if you've got a nuclear weapon flying directly over the Earth, over some enemy, and you want to deploy your nuclear weapon, you just have it deorbit, and within minutes, you are nuking their cities. And that was too quick. All the nations agreed. That was really scary. And so they made it that it's a violation of the Outerspace Treaty to put any nuclear weapons into space. No nuclear weapons on the moon. No nuclear weapons on Mars. No nuclear weapons. Now, there's a bunch of other issues as part of the Outerspace Treaty. You can't own parts of space and so on. But they didn't really cover planetary protection like this. So unless like the tardigrades are nuclear powered super soldier tardigrades, then it's not a violation. Now that said, there is sort of this increasing concern about planetary protection, both us infecting other planets like Mars with our Earth life. Cyanobacteria can take over anything. Maybe it can if it gets its, leafy claws into Mars or Europa or Enceladus, then maybe it can spread out and go wild, but also for things to come back to Earth. So if we perhaps do the Mars sample return and we bring Martian bacteria back to Earth, do we risk introducing a novel bacteria into Earth that spreads like wildfire and our native plants and animals and bacteria have no experience with it and it's War of the Worlds, but reverse. Anyway, so there is kind of a growing call for planetary protection, and there's been an international community. NASA has a department for planetary protection, but there's a sort of growing international community from the European Space Agency, the Russians, the Chinese, and so on, to start considering international rules on planetary protection. So we're kind of in a state of flux right now as there's more and more space missions happening. The space lawyers are starting to catch up with the capabilities of Earth. And I'm sure we're going to see some more firm regulations. I wouldn't be surprised if we see like a new version of the Outerspace Treaty come out in a few years that tries to nail down these kinds of issues in the future. Alexandru Vataman. Hey Fraser, how come all the planets in our solar system are spinning around the sun with the right speed? Not too slow to fall on the sun and not too fast to leave the solar system at all. Thanks. Yeah, isn't that a weird coincidence that all of the planets in the solar system are in perfect balance? I mean, think about the forces that are acting on each one of the planets. You've got the gravity of the sun pulling them inward. If the planets were not orbiting around the sun, they would just fall, right? They would fall down into the sun and be consumed. They are going sideways. And when you think about, say, you spin a bucket of water around your head, it pulls out tight because you've got the orbital velocity is providing a force that's going outward. And the outward force from the orbit perfectly balances the inward force that's coming from the sun, and these things just remain in perfect orbit. And like the question is like, wow, like how did this all happen? And so it all happened because anything that wasn't in perfect balance is long gone. And so when you sort of roll the clock backward all the way back to the beginning of the solar system, you've got the sun in the middle, you've got this disk of material that is forming around the sun, and the whole thing is rotating. And then the sun, as it gathers in its material, it's spinning up more and more quickly and ignites in solar fusion. You've got all of these planets forming out of this, and they're all, when you think about this whole cloud that's going around the sun, this whole cloud is in perfect balance. The gravity of the sun is pulling the particles inward, their rotation around the sun is pushing outward, and everything is perfect balance. So kind of like the answer is that everything started out balanced and everything has remained in balance this entire time up until today. And anything was out of balance, maybe it got too close to another planet, maybe it got too close to the sun, went through some kind of three-body interaction, got kicked out of the solar system, or gobbled up by the sun, or crashed into Jupiter, or what have you. And so what you're seeing today is kind of survivor bias of the entire solar system. Everything that remained in balance and didn't get destroyed and didn't get eaten up and didn't get kicked out and didn't interact is still here. Dean C. Is there a Hubble-level telescope in the International Space Station? Absolutely not. The space station really is used as a way to do experiments with human beings, with materials inside the confines of the International Space Station. That said, there are a few experiments on the exterior of the space station. Not a telescope exactly, but there's a couple of instruments. One that's really cool is called NICER. It is a experiment that's designed to scan neutron stars and detect the signals coming from them. And one of the cool sort of side projects that NICER did was that it was able to essentially map out the pulsars around us in the Milky Way And it was able to navigate the position of the International Space Station based just purely on the signals coming from all of these pulsars around it. So occasionally there are various experiments that are put on the exterior of the International Space Station, ones that test how well life can survive out in space. This nicer, as I mentioned, and there have been other experiments and will be more in the future, but definitely not any kind of real space telescope. Those are all launched separately and fly on their own. I'm not sure it would make sense to attach a telescope to the space station. I mean, the space station is a machine. It's got fans that kick on, radiators. It's got spacecraft docking all the time, astronauts bumping off of walls, and any of that would mess with the really fine optics, the long exposures that a space telescope is looking to do. So nope, no telescopes on the space station. Sean Mock, why and how does the solar maximum work? Now, I'm not entirely sure scientists fully know the answer to this, like why the solar maximum. So the solar maximum and the solar minimum is just this explanation of this cycle that the sun goes through. It's an 11-year cycle. And so the sun starts out with very little sunspot activity, very little flare activity, coronal mass ejection activity, and then over the course of 11 years, the activity rises and rises and rises to the solar maximum. And then it turns around and the activity goes down and goes down until the surface of the sun is almost completely clear of sunspots. And during solar maximum, you get lots of big sunspots, very powerful flares, coronal mass ejections. We get more auroral activity here on Earth. Occasionally, events that disrupt our communications and electrical grids and so on. But just in general, you get this 11-year cycle. So it's like 22 years to do the full circle. And it's a rough approximation. I mean, you can have the solar maximum start or the switch start a little later, come a little earlier. The power of the minimum or maximum can change. But in general, that's what astronomers see. And what happens during that process is the sun has a magnetic north pole and magnetic south pole, just like the Earth does. And you've got these magnetic field lines. And over the course of this 11-year cycle, the magnetic field lines start to shift. And they actually flip over the courses of these 11 years. So the sun's north pole becomes its south pole, and its south pole becomes its north pole. And you get these tangled up magnetic field lines, and so increased activity. And like, why? That's an unsolved question. Why it takes that period of time, we don't really know. It has something to do with how different layers on the sun rotate at different speeds. But this is why a fleet of spacecraft, including the Parker Solar Probe, Solar Orbiter, have been sent to the sun. Why we've got powerful new observatories here on Earth, like Daniel K. Inouye. We've got SOHO. We've got Hinode. We've got all these spacecraft that are observing the sun to try and figure out all of these secrets from the sun. But we're on our way to solar maximum right now, and that means more aurora activity, and that's always a fun thing. So enjoy it while it lasts. Ryan Dougal. Should the British pursue space-based solar power like they plan to? I've been reporting on space-based solar power for quite a while. This is the idea that you put a satellite out in space that is catching the sun's rays 24/7, and then you beam them back down to Earth using microwaves. And from what I can tell, and a lot of people that I've talked to, it just doesn't make sense that the price of solar panels down here on Earth is so low that it just makes more sense to set up solar panels on people's roofs and harvest the electricity directly, or cover giant chunks of the Sahara Desert and then take that power up to Europe. To launch a rocket with solar panels is incredibly expensive. You're looking at thousands of dollars a kilogram, tens of thousands of dollars when you sort of include the construction and all of that for power, when there's mountains of it down here on Earth. Even though you only get it for half a day and you don't get it when there's bad weather and so on, still. So, we've seen people talk about this for decades. And all the while, the price on solar panels comes down and down and down, faster and faster and faster. To now, like, Earth-based solar electricity, renewables are the cheapest. Cheaper than coal, cheaper than oil and gas and any other solution that you may want. So I really can't envision a time when it makes sense to put satellites in orbit and beam that power back down to Earth. Now, that said, there are some really good reasons to beam power in space, but to other satellites. So you can imagine situations like, say, you've got rover or a base on the moon in the permanently shadowed craters on the moon. And then you build a power station that is in the permanently sunlit portion of the moon, and then it beams the power to, say, the rover that's crawling around, or beams it to the station if it's too far to run a cable. You can imagine situations where you've got spacecraft in space that are going to spend some time in the Earth's shadow, and you could set up satellites that are going to beam power to these satellites. But to beam back power back down to Earth, it really just doesn't make financial sense to do it. More questions in a second, but first I'd like to thank our patrons: Millie Lopez, Christian Gabor, Esther Lee Davenport, Lindsay Forbes, Avi Saskin, Alex Poiret, and the rest of our 820 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Sprinter 768. Does a rocket bound for anywhere in the solar system have to go into an orbit around the Earth before heading out, and if so, why? No, you don't need to go into orbit around the Earth before you head off to some distant destination. And very rarely do we do that anymore. Like when spacecraft are sent to Mars, they just do a direct flight. Well, they do a special trajectory called a Hohmann transfer that interacts the orbit of Mars at the appropriate time. But this rocket is sent directly there. Same thing when spacecraft was sent, say when the Parker Solar Probe was launched, or when Cassini was sent out to Saturn. Now, Cassini had to do some flybys of some parts of the inner solar system, but just in general, you don't go into orbit around the Earth. The only time that you actually had to go into orbit was during the Apollo era. They would send up the spacecraft. It went into orbit around the Earth a couple of times, and that gave the astronauts some time to maneuver. They had to do some docking maneuvers to bring out the lunar lander, shift around, connect it to the command module, and then discard the rest of their upper stage, and then do a burn that took them to the moon. And you can imagine when Starship starts to fly, it's going to go into orbit, and then follow-on spacecraft are going to go into orbit, and they're going to refuel the starships, and then they're going to, when the fully refueled Starship is ready to go, it's going to fly off to Mars or to the moon or whatever. But in general, no, rockets take a direct flight. They just launch off the Earth. They are already on an escape velocity from the Earth, and they go towards their destination. Peaks and pokes. When will we send a microscope to Mars to search for life? So there hasn't been like a really powerful microscope sent to Mars yet. But there has been a pretty good microscope type instrument sent to Mars. So on the Perseverance rover, it's got that long arm. And at the end of that arm, it's got this instrument called SHERLOC, which stands for the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. The nickname is SHERLOC. And its purpose is to do fine-scale detection of minerals, organic molecules, and potential biosignatures. And it's like a very, very high quality, very high resolution camera. It also has some other instruments as part of this camera system. And it uses it at the end of this robotic arm that it can use to sort of shift around and look at different objects. And it provides a fairly high level. It can see objects as small as 10 micrometers, which is pretty good. Now, it's not going to be the level of a microscope to see bacteria, things like that. But this is like the next level. It's the highest resolution, best microscoping imager that's ever been sent to Mars. For like the next level, I mean, when the Mars Sample Return mission arrives, it's going to be gathering up all of these samples that Perseverance has been collecting. It's going to gather them up, and then it's going to bring them back home to Earth. And then planetary scientists are going to be able to examine these samples with the most powerful Earth-based instruments. Electron microscopes that weigh a ton, right? You've got these incredibly powerful microscopes, all these instruments here on Earth to do a really proper job. Now, you can imagine some future where a proper laboratory is set up on Mars with researchers sent to Mars, and they're bringing samples back in to their habitat, and they're examining them under the microscope. And then you'll have some serious analysis. But until then, it just doesn't make sense to send a really powerful microscope to Mars. It would just be like the only instrument that you could carry on board. And you wouldn't be able to do, when you think about all the preparation, like a scientist will go and take an object and they'll grind it up and they'll slice it up and then they'll mix it with liquid and then they'll flatten it out on a little tray and then they'll put it into their microscope. Like, there's a lot of work to properly use a microscope, and there's only so much you can do with a rover. So not yet, but I'm sure when the humans finally arrive on Mars, then we'll have a proper microscope. Unexpected. Could gravitational lensing help us to see objects beyond the visible universe? I don't know if you saw the news this week, but the Hubble Space Telescope saw the most distant star that's ever been seen. The light from this star had been traveling for 13.9 billion years. It was emitted like 800 million years after the Big Bang. An individual star seen by Hubble. And the only way it could do this is with gravitational lensing, where you had this galaxy cluster in front of the galaxy that had the star. And this cluster, this foreground object, acted like a natural gravitational lens that imaged the background object and brightened it and allowed Hubble to be able to even spot it. And Hubble's done this many times. The most distant objects that Hubble's been able to see have all been thanks due to gravitational lensing. But there's a limit. And the limit, of course, is the cosmic microwave background radiation. Not because of distance, but because of time. The cosmic microwave background is the first moment in time when light was able to be released out into the universe. You can't see beyond that because earlier than that, the universe was opaque. So there's nothing that will allow us to see visually beyond the cosmic microwave background radiation. Now, maybe we can see beyond it with gravitational waves to see that additional 380,000 years to the Big Bang. But then that's it. That is the farthest that we will ever be able to see out in our universe because we are looking backwards in time. You're looking in all directions, at every spot, to the very beginning of the universe. And so how can you see something that is beyond the beginning of the universe? We won't be able to do it. So nope, gravitational lensing won't let you see beyond the visible universe. Nothing can. Jonah Wolfson. Hey Fraser, what other worlds in the solar system can we expect to see high quality photos like Curiosity from the surface in the coming years, decades? Thanks. There are a bunch of spacecraft in the works, but I mean, a lot of the places that are in the works we've already seen, but I'll give you a few that are coming. One is the Japanese are building a spacecraft that's going to be going to Phobos, which is one of the Martian moons. So we'll be seeing the surface of Phobos for the first time. Now it's going to look like an asteroid. It won't be that interesting really, but you know, we'll know that we're looking at Phobos. That's pretty exciting. We've got NASA's Europa Clipper mission, which is going to be doing a very close mission to Europa, providing us images of the surface of Europa at higher detail than we've ever seen before. Now, we've seen Europa, so it's going to be ice, but closer, but hopefully we can see cracks in the ice and craters, and maybe we'll be able to see ice spires and places where water is geysering out of Europa. That'll be incredible. We've got 2 missions going to Venus, which are going to be improving the resolution that we can see of the surface of Venus significantly. But I would say the one that I'm most excited, the one that's going to give us just this utterly new view of a place, is going to be the Titan Dragonfly. And that's, of course, this nuclear-powered helicopter that's going to be going to Titan in the next decade. It probably won't arrive until the mid-2030s. But when it does, it's going to be down there on the surface of Titan, flying around, looking at boulders and looking at various features and looking inside craters. And the few pictures that we have of Titan that were taken by the Huygens probe that came along with Cassini showed just this absolutely alien landscape. But we have just like this one image that was taken as the probe was hitting the surface. But now we'll have this helicopter that's going to be just nonstop flying around, sending back all of these pictures. It's going to be mind-blowing. So that is the one that is going to change our perspective of the surface of a planet. It's as exciting, more exciting, as like when we were going to get those first images from New Horizons. Like we'd never seen Pluto before, and now we were about to finally see Pluto. Well, now that's old news. We've seen Pluto. But now, soon, we will be seeing the surface of Titan in great detail. That's the one I'm excited about. Innocuous remark. Love the channel. In the distant future, when the cosmic microwave background has a longer wavelength than the universe, could a very fast moving ship detect it anyway due to blue shift? I've always wondered. Okay, so the cosmic microwave background is currently in the microwave spectrum, but when it was first released, it was at a time when the entire universe had just cooled down to the point that it was no longer blocking, no longer opaque to light. And sort of visually, imagine a giant red star. That was what the entire universe looked like, except it was everywhere, not just like the surface of a star. But imagine that. And then over time, over the 13.8 billion years that the universe has been expanding, that wavelength has grown from what was in the nanometer realm to the, into the microwave realm. And over time, it's going to keep, those wavelengths are going to keep stretching and stretching out into the radio. And then the radio waves will be meters long, and then kilometers long, and then light years long. And so one possibility is that you can be in orbit around a black hole. And as you're in orbit around the black hole, then you're going to experience time dilation. And so you will see the universe brighten because you're experiencing essentially a sped up universe, which is one way to think about it. And then the other possibility is that you will fly in your spacecraft in one direction. And according to Einstein, as you fly, the wavelengths of light in front of you, blue shift, and the wavelengths behind you, red shift. And so, yeah, you would be able to kind of roll back the temperature of the universe as you flew. Now, I don't know whether you could get to the point that wavelengths the size of the universe, but you could definitely bring back the cosmic microwave background photons from really redshifted a little bit more into the blue, maybe to the point that you could observe them. You can imagine some future astronomers where they just get this sense that there's this cosmic microwave background, and what they do is they send a spacecraft that goes close to the speed of light, and they put a telescope on it so that it can make observations that would have been easy for us today. Maybe that's a science fiction book. I like it. Sunny Vegas. Nuclear fusion produces heat. Does it mean that it needs a fuel, hydrogen, to burn in order to create thrust? Do nuclear fusion rockets still need fuel? So there's really kind of two parts to a nuclear rocket. You've got the fuel to create the reaction. So imagine you've got a fission rocket. We'll start with that first. So you've got, say, uranium. You are breaking up the uranium, or plutonium. You're breaking up the plutonium, and you're releasing energy. You're releasing heat. And then you use that heat to superheat some kind of propellant. Usually it's like hydrogen, and you blast that out the back of the rocket. And so you can imagine fusion, it would be sort of roughly the same thing. You've got your fusion reactor, you're feeding it with hydrogen, you're fusing it into helium, you are generating enormous amounts of heat, and then you're using that heat to heat up a propellant and blast it out the back of your rocket at high velocity. And that's what gives you your thrust. So in both situations, you've got the reactor generating the heat, and then it's sending off some kind of propellant. 8 Tennyson. Does time travel slower in the center of the universe? We've talked about this idea several times in the past, that there is no center of the universe. Every part of the universe is the center. And you can go back and look at those episodes, do a search on my channel for center of the universe, and you'll find them. But there is no center of the universe. But sort of the question I guess you're asking is, like, would time travel more slowly where there's a lot more mass? If you've watched Interstellar, if you spend too much time near a supermassive black hole, then you know that time slows down for you compared to the rest of the universe. The universe speeds up from your perspective. And so if there was a center of the universe, which there isn't, and there was like some big ball of mass there, and you were close to it, then time would go differently. But this idea of time dilation happens across the entire universe. Because of speed, you've got parts of the universe are moving away from each other on opposite directions, at one side of the observable universe to the other side of the observable universe. You've got about 30,000 years of time dilation between those, just because of their motion. And if you spend a lot of time near a supermassive black hole, you would experience other forms of time dilation because of gravity. When you just walk around, you're experiencing time dilation from your movement, and you're experiencing time dilation from your mass. When you climb up the top stairs, you are further away from the Earth's gravity, and so you are experiencing a different amount of time dilation from somebody who is down at the bottom of the stairs. Relativity is a weird thing. Stubby 1085. I've heard that if black holes have a Planck star center, they will eventually go supernova. What would a supernova for supermassive black hole be like? There's no reason to believe that a black hole is going to go supernova. There's no possible way. Imagine, right? The force of gravity that is holding a black hole together is so strong that nothing, not even light, can escape it. You can't explode as a supernova. Gamma radiation can't escape out of it. Material, debris, nothing. Once it becomes a black hole, there's no way back. Now, the idea of a Planck star is that maybe, you say you've got a neutron star, which is already a very compact object. You've got all the protons and the electrons mashed together, and they are sort of forming this ball of neutrons. And then maybe it's feeding off of some companion object and gathering more. And maybe then it reaches some limit that makes it compress down one more step and moves into a smaller object. And we don't know. They're called like strange stars or Planck stars. And we don't know if these things can possibly exist. And then if this object continues gathering more material, then maybe it finally collapses that one more step and becomes a black hole. But once it's a black hole, the only way it's ever going to die is through Hawking radiation, through slowly evaporating its mass over the entire lifetime of the universe. All right. Those were all the questions that we had this week. Thank you, everyone, for asking them on the YouTube channel and for showing up during the live show. And remember, we've got these live conversations that are going to be happening on our Discord channel. So we'll have a link to that here. You should come and join us, talk about cool concepts in space and astronomy with each other, with me. It's going to be a lot of fun. All right. And we do this show every Monday at 5 p.m. Pacific time live. So if you can, come and join us. All right. We'll see you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.